Hey everybody. So this paper is addressing another one of those concepts that I've been telling you on this channel for a few years now. I've been talking about up and down and then staking my claim very specifically that I bet against and I have been betting against the billion-dollar companies, all of like the big AI companies, etc. within this, which is very simplistically and boils down to that the data set itself, like the data set is a platonic construct, right? Does not exist. It's not actually what the models are learning off of, and it's like basically almost irrelevant overall to the entire equation, right? And then I've gone over this up and down. You could watch a million of my videos at this point that go over that. And then oftentimes, when I first started making claims along these lines, like people would say, well, if that's the case, then it will come out in mainstream research, right? And then here we are, where basically, I mean, like literally everything that I've been telling you for 3 years now has like multitudes of mainstream research behind it. Here's one addressing what I just talked about now, which is Reconstruction Alignment improves unified multimodal models. And this particular paper is put out by UC Berkeley and the University of Washington. They release a project page for their GitHub, which you can check out. And then they release a lot of models, like overall, right? So I want to highlight and point to these resources that they do off the top. So they train up to a 1.5 billion parameter model on this, which is like higher scaling than I've done within this, right? So that's, I mean, like could be the one knock within this with my research is I never scale these things up that high because I'm not investing my own money into these things, right? I don't like UC Berkeley, University of Washington. Again, like you're right. If I'm right, if it's mainstream, then it'll come out in the mainstream research. So here we are. They've done the scaling for me. So I'd save me the money, right? So let me go ahead and just go through the abstract here, right? So unified multimodal models, or UMMs, unify visual understanding and generation within a single architecture. However, conventional training relies on image-text pairs or sequences whose captions are typically sparse and miss fine-grained visual details, even when they use hundreds of words to describe a simple image. We introduce Reconstruction Alignment, or RECA, a resource-efficient post-training method that leverages visual understanding encoder embeddings as a dense text prompts, providing rich supervision without captions. Concretely, RECA conditions a UMM on its own visual understanding embeddings and optimizes it to reconstruct the input image with a self-supervised reconstruction loss, thereby realigning understanding and generation. Despite its simplicity, RECA is broadly applicable across autoregressive, masked autoregressive, and diffusion-based UMMs. It consistently improves generation and editing fidelity with only 27 GPU hours. Post-training with RECA substantially improves image generation performance on Gen Eval. There's showing what's that like a 17% increase, and DPG bench, like that's like 8% increase, while also boosting editing benchmarks. Few points. And then notably, RECA surpasses much larger open source models and applies broadly across diverse UMM architectures, establishing it as an efficient and general post-training alignment strategy of UMMs. Their method, very flat out, exactly what they're talking about. I mean, this is what I've been talking to you for 2 years now. This is exactly what my Zyra architecture is extensively based off of. I have so many Colab notebooks that I've shared with you and could share with you at this point that go over this exact concept. This is how I measure these things, right? And how I go over and look at these things and employ this method within my head, right? And it's to me, just starting off at the base of this, I started off at a very simplistic level, right? Which is that these models, no matter what the model is, its a base language is not English, and then also its base language is not mathematics. And then I arrive at those two things because its base language isn't English, we know that. And then its base language isn't mathematics because the models don't internalize mathematics on any level, right? They don't internalize, at least on a broad enough level. Maybe they do do on, I can't say that they don't on any level whatsoever. Like I like my experiments and data show that they have some internalization, but it's not the internalization in the same way that a human would be, right? They don't have like a full internalized tool usage and symbols like and all of that, right? And then so all of that means that their base language is something that is more simplistic than that, which is geometric shapes, and then all playing around with those geometric shapes, and then there's kind of a emergent geometry that comes from that. And then I essentially trace all of that through its roots and its sources, right? And then it's like in philosophical terms, the best philosophical example that I can think of to wrap my head around that is Platonic forms and everything that is associated with that, right? But that's secondary, applying the philosophy to it after I understand exactly what's going on within these physics, and then it's like, well, like, okay, that's the best example I've ever heard of in any philosophy or any concept whatsoever that I can actually equate like what is actually going on within this, right? And then when you do this and you test it out, it works extensively, right? And then so the title of this notebook is very straightforward to me, right? Which is like you need a data set to train your models. That's pretty noobish, right? I don't need it. Like, so this particular model that we're looking at here, what makes this particular notebook special in this instance is that this model is never actually given the actual data set whatsoever, right? It's given the exact principles that they lay out within this research paper, which is a reconstruction of the data set, a lossy reconstruction of the data set, but it's a reconstruction of the data set that is in line with the model, right? It's the model takes this data set and then creates embeddings off of that data set. Those embeddings create a shape. That shape is then put through multiple dimensional shape, like transformations through the model, like up and down, right? 2 dimensions up to like thousands of dimensions. And then within that, whatever stays consistent within that shape after those dimensional transitions is essentially what the model is reading and learning off of, and that's its embeddings, right? And then so like as long as you can get that right, just whatever those embeddings are, then the model can learn off of it, and then you can get those embeddings and then peel those embeddings from the data set in like 7 seconds. Like so then essentially what I do with this particular model that we're looking at here is just take those embeddings, create we'll call it a graph, like a 2-dimensional graph off of those embeddings, and then that gets me the shape of the data set. And then the model just essentially learns off of the shape of that data set, right? And then so in this instance, it's Fashion-MNIST. And then in the end, it gets it's calling it 76% accuracy. But I want to call out a few things here with Fashion-MNIST, right? Here's a sample of the data set. It's getting it pretty flawlessly, right? Sandal. This second one, it got it wrong because it predicted that this is a t-shirt top when it should have predicted shirt. Second, this one it gets right, pullover, trouser. This one right, right. And then this one is another one where it gets wrong. It predicted coat, and this is a pullover. Okay, I don't know. I mean, it looks like a coat to me, or a pullover, I guess, right? But so I can like, okay. And then this one, it predicted a t-shirt top when it was supposed to predict shirt. So again, like it's these ones, like these. It's not like just, like making up random stuff. Like these are things that I would mispredict on this and this. So these are like issues with data sets, and then with this particular data set in general, and then just highlighting that right. Like that's what's dragging it down to 76% accuracy. So when you see the 76% accuracy up front, you're like, that's not anything. But like, look at exactly what it's getting wrong. It predicted t-shirt top as opposed to shirt. It predicted that this is a coat as opposed to a pullover. Like that's what it's getting wrong, right? Like, I mean, and then all of this is without it actually, like, no labels. It doesn't know what these labels are, right? That's the other thing too. Like, it doesn't know that there's a labeled t-shirt top and then one for shirt. Like, it's never given that specific information to train on, right? And then so that's literally what this paper goes through. And then so instead of just me telling you, hey, this is what it is, here's UC Berkeley, University of Washington. They give you models scaling this up to 1.5 billion parameters. They have a whole project page on their GitHub that is very extensively built out, giving you additional code, models. They give you a full-on demo. Here's all of the researchers involved with this. And then, I mean, here it is, and here you go, right? And then, like, all of this, as you can see, it's all related to in this instance, and these what we're talking about within this, it's all image models, right? It's like image classification is what we're dealing with very specifically within this, but this has broad applications beyond all of this. Like so to me, and with all of my research, combining all of this, the best thing that I can tell you, like all of this combined within this, like kind of the next step within this, right? Like is that all of this works and wouldn't work if the core principle of this weren't true, which is that all of these models operate off of diffusion at their core, right? No matter what model it is that we're dealing with, whether we're dealing with CNN models, like what we're talking about within this particular instance, and classifiers, or we're talking about transformer models, or we're talking about pure image generation models and pure image editing, all of them have the same underlying principle, which is that underlying principle is diffusion. So all of them are essentially, they have physics principles. They're all bound by physics. And then within that, like there's a lot of physics principles and understanding of physics. Once you understand physics, that you understand fully the limitations, and then what can be pushed up against, and then what are boundaries and unknowns within that, right? Like there's a lot of knowns within physics, and then so a lot of things that you just flat out can't do. And then it's like, if you know it from a physics standpoint, it's like you can see people like I don't know, like on like Reddit or something, right? Well, they'll be like, oh, this is like I think I could do this, and it's like, well, no, you can't do that because of physics, dude, and you just like don't realize that. But like once you get past that, like this, it's to me the secondary layer within that is that like there's a huge element of physics overall that is still unknown, and we still don't understand, and we still don't some things around diffusion, right? And then like things are all around that overall, which is kind of like what leads us to where we are overall. So like, while yes, layer A is that the general public has kind of a not an understanding of physics whatsoever. Layer B is that physics doesn't have an understanding of physics whatsoever. Is kind of how I look at it overall, right? As kind of the grand scheme of that equation overall. But here we are, this research paper, 28-page research paper now, telling you again, another concept that I've been telling you for multitudes of years now, that if I'm just not talking out of my booty, then it would be somebody that would, come up with this research and validate these claims on a kind of broad level, right? So here we are, there's more and more research around this. Like, I can't state this enough. Like, yes, very specifically, and in a singular sentences, like all of the people that went hard on data within this, they're losing their shirts. Like they wasted, and like billions of dollars evaporated. I can't state that enough. I have been saying that that's exactly what's going to happen within that. Like, just because a bunch of smart people are going in on that equation doesn't mean that they understand this equation, right? This equation and understanding it to this level takes a lot of digging in order to get to it, right? And then before you get to this layer, it's all data. Data is everything. So you invest into the data layer, but then once you chip past it, then there's a layer deeper than the data layer, and it's like, well, if it's a layer deeper than the data layer, that layer has kind of governmental control over the data layer itself, right? That's just kind of how it works once you get deeper than it overall. And I didn't do it. It's just how it works out. And if you actually reason it out and you actually apply physics to these things and bring them to their end conclusion, here we are. I've been telling you for 2 years now. And then if you like this type of content overall, please like and subscribe. Thanks very much.